So yeah.
It's the same thing with the big gray block again. Yeah, okay.
Yeah. No, I mean, I'm juggling with these screens, but I think now we are okay.
Okay.
Did anyone get a chance to look at the two questions we had on our little group? Did you guys see what Archimedes and Eudoxus did? There was once, so let's just start with the second question first. Any thoughts about how you would go about doing 2/5 plus 4/25 plus 8 1/25 and so on? I mean, it's really about the recap that I have. So, we started looking at this method of exhaustion that is really about this one. I mean, you have any, I mean, are you guys okay with this that this indeed is 1/3 if we see it by the method of exhaustion?
Yeah.
Cool. And how about this one? We really had, right, 2/5. So I think, one way to look at it is perhaps this. Are you able to now see that this indeed has to be 2/3? If you see, then what are we doing at every time? What we're doing is that whatever is to be distributed, we are making 5 equal parts of it, right? And if you look at those 5 equal parts, then we are going to leave those 2 parts undistributed. And out of these 3 parts that are to be distributed, we receive 2. So which means we receive 2/3. In the first step, are we on the same page? Is everyone clear about that? Or
Yeah,
let me ask.
I'm trying to understand it, but I'll just follow along. Maybe I'll understand it later.
No, that's fine. I think we can spend a little bit more on this. See, what we are doing is that we are making 5 equal parts, right? And what we're saying is that out of those 5 equal parts, we will leave 2 parts alone. We're not going to distribute that. We will make this a sort of unending process of distribution. So what we're saying is that I'm in the first step, I'm getting 2/5, right? But that 2/5 is really 2/3 of what is being distributed. So in this first step, I'm distributing 3/5. So 2/5 is really 2/3 of 3/5, right? So in the first step of distribution, when this particular part is gone from the entire rectangle that I had to begin with, only these two are remaining, and I'm getting 2/3. And the point is that the same thing happens here. So what I have now left is 2/5, right? So out of that 2/5, I'm again getting, I'm leaving 2/5 behind. So 2/5 of 2/5 is 4/25, and so I have got 6/25. I mean, we do the subtraction, and then we get again 2/3 of what we decide to distribute. So at every distribution step, we are just getting 2/3. And so the argument is that at every step I'm getting 2/3 of the thing that is being distributed, 2/3, 2/3, 2/3, just basically 2/3 all the time. And the argument that Archimedes made, which was the correct one, that was that when we would have done these infinite number of steps, ultimately we would have 2/3. And I do want you guys to spend a little bit more time if it's not clear to you. You know, the argument is just basically an infinite process of distribution. And one other thing about science or mathematics is that there has to be consilience. Consilience means coming to the same conclusion when you're trying to solve the problem or answer a question in many different ways. When there is a concordance or when there is some kind of an alignment in the answers, we believe it. So you, for example, in science, it's like about carbon dating. Um, the way they decide the time of a particular fossil has to match in some ways. Two different techniques, three different techniques have to just match. If there is a tremendous discrepancy between them, then there is a problem. Same thing in mathematics. Now, if this way here, 2/3 is the answer, when we, you guys have studied geometric series, at least, some part of it in your early high school or maybe late middle school. And we know that this is just, if A is the first term, R is the common ratio, then it is A upon 1 minus R. And A here is 2/5, R is also 2/5, and you get 2/3 upon 3/5. It's a 2/5 upon 3/5, so it's 2/3 basically. All the answers basically point to the same answer, same value, and so that way it gives us the confidence that we are on the right track. But try to follow this. And the second question that we had asked was, what's your own thinking about why 1/2 plus 1/4 plus 1/8 plus dot 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 won't exceed 1. It just is not possible for this sum to exceed 1, no matter how many terms you add. Why do you have a personal connection with this? I mean, I do want you to spend some time on this one. See, we know that the answer is 1. When we add 1/2 plus 1/4 plus 1/8, the infinite sum is 1. But I'm asking a question before that. Why is it that the sum will never exceed 1? It's like, it's like that line that shall not be crossed. In Indian mythology, we had what we call Lakshman Resha, right? If you guys have read about Ramayana, then you perhaps remember that there was this line. Here, similarly, we have a line, and the line is 1. But what is the argument? That I'm adding infinite terms here, and I'm still not crossing the line that whose value is 1. What will happen? So try to make arguments with respect to that and try to discover your own ways, because I can give you the answer that I have in my mind, but I don't want you to be influenced by that. I really want you to do this exercise. I urge you to do this exercise. Why is it that we are adding infinite terms? They're small. Every term is smaller than the previous term. In fact, every term is half of the previous term. But still, there are infinitely many terms. And we are sitting here and saying that that sum is not going to exceed a finite number like 1. This is a big deal, and I want you to be comfortable with that. Okay, so those were the two things. Yeah, I think Swara had to say something. Sorry, I didn't look at the screen. Go ahead.
About like the adding 1/2 and 1/4 and then so on. If you just think about like a square and you fill in half of it, and then of the leftover space, you fill in half of it. So since you'll always be filling in half of the remaining space, you'll never actually fill in the whole cube. I mean, the whole square. That's my take on it.
Yeah, I mean, so is this convincing enough for you that it has to be half of the? So what if I just started adding a smaller term, like let's say, let's just take the natural numbers and their reciprocals, like let's say half plus one third plus one fourth, and so on. So every term is smaller than the previous. It's not half of the previous term, but still smaller. What happens in this particular series? Do you think that it has it do you have a number in your mind that this particular series won't exceed?
I'm not so sure about that. Like the half one makes sense to me.
Right. So there must be something unique that is happening when we have a ratio between successive terms. And I want all of us to be very comfortable with that. As long as we have a ratio, there's something magical. There's nothing magical really, but when you look at it for the first time, it appears magical. That something magical happens. When the subsequent term, or every term is in some ratio with respect to the previous term, and that ratio is maintained, something interesting happens. Suddenly the Lakshman Resha starts appearing, and that, to me at least, was very interesting. This does not happen when there is no ratio. So if you, I'll tell you, we are going to discuss this a little bit later, but I'm just telling you that if you just have 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 and dot plus dot dot dot, this sum does not, there is no number that this particular series will not exceed. You can tell me a number however large, and I can tell you how many terms to take like this to exceed that number. I mean, this is just amazing, right? I mean, something happens when there is a ratio that is lost when there is no constant ratio. And Greeks knew this. Greeks knew 2000 years ago. The point is that we wanted to make this really concrete. And why calculus is somewhat difficult, or somewhat we don't make the connection, is that we took time to solidify these things. It was not very easy. People, mathematicians came up with intriguing questions on their own, and finally we seem to be on a solid footing. And that's where we have to, like it or not, I hope you like it, that we need to bring in some rigor. All these conceptual things are very, very interesting. And for us to stand on solid footing, we need some rigor. We need to at least, stress ourselves a little bit so that we can answer difficult questions confidently. And so I think, we are still going to spend some more time on making sure that the functions and their limits are properly understood, at least in this way of dealing with things. This way of dealing with the things has got a name, and we call that standard analysis. Now I'm giving you slightly jargonish terms here. Please forgive me for that, but I think it's important to know this, that in a particular way of doing things, we have to introduce limits of functions. So I think, I have to ask Apurva to continue, and please, ask questions if something is unclear. We should try. I mean, this particular group discussion is for that. I mean, this is quite unlike our other classes, which are also important. But this is more like a supplemental thing. Here we come and we ask any question. There is no bar. This like we're not blocking anyone from doing something which might look stupid elsewhere. Again, I have said this several times. I'm going to repeat it once more. Stupid is the question that is not asked. All right. So with that, I just want us to get a little more rigorous, a little more technical. So I'll stop sharing.
Okay, I'll share my slides. Okay, can everybody see?
Yeah,
See my slides, right?
I can see it. Yep.
Okay. Yeah, so previously we went over this very interesting function, and we came to an agreement that we at x equal to 0, we don't know what the value will be. So we just call it undefined. And similarly, we don't know what the limit of the function sine 1 by x at x equal to 0 will be either. So we also say that's undefined. Right? We came to this agreement. But, and it's fine to say that when we call a limit, so far when we don't know what a limit is, we say it's undefined. Right. And there's nothing wrong with that. However, there is a better way to say this. We can say that the limit in question, we say it does not exist, or DNE, right? We say, and they're both correct. You can say undefined, and you can say the limit does not exist. But usually we say that the limit does not exist rather than it's undefined. Um, I think it's just a convention because if it is undefined if it does not exist, but we just say the limit D and E is just it's just common. What is usually said, yeah. Okay. Um. Yeah. So when we think of limits, right, we think of the input variable, right? Input variable, such as the input of a function. When we're thinking of limit of the function, we think of that input approaching a value. But there's not only one way to approach a value, right? We can approach it by either increasing or decreasing x toward the specific value we want to approach, right? So yeah, we call these different ways of approaching the different limits that are created, right? When we try to approach a specific value from the left or the right, we call them one-sided limits. Okay. Now, this is just a it's not a very difficult topic, but it's something that's important because well, I will see that ahead. So the point is when you increase x to approach a value, right? We call it the left-sided limit. And since you approach it from the left, we say that the limit as x tends to L from the left is whatever the limit is. And there's a notation for that. Instead of saying limit as x tends to 0, for example, we say limit as x tends to 0 minus. It's a little superscript minus that we say right after 0. As x tends to 0 minus means that from below, x is increasing towards 0, and the limit as we're trying when we try it, and in this case we're trying to find the limit as x approaches, as x increases toward 0.
Yeah, in the diagram, however, I think you're doing it at x is equal to 2, I believe, right?
In this case it's x is equal to 2. Yeah, when
Yeah.
x is
Okay.
tending to L specifically.
Right.
And in this case L is 2. Yeah. So L is some specific value. And
It's some real number.
yeah, some real number. Yeah, and you can also decrease x to approach the specific value, and you can decrease x to approach L, and we call that the right-sided limit. And since you approach it from the right, we say that the limit as x tends to L from the right is, whatever the limit is. Instead of writing limit as x tends to 0 minus, we write limit as x tends to 0 plus, and that means x is decreasing as it approaches L. So yeah, in this
X
case it's
approaches
2.
A, not L, right?
Yeah, in this, yeah, any specific value
Right.
basically. And yeah, so in this case it would be just
So L is the value of the limit, which is basically value of the function as x approaches A, as it is typically called, right? So I'm not sure if your slide has some error here. X less than L.
yeah,
X does not approach L, right?
no, as the input, right? In this case the input is x.
But I
Input
thought
is
that L was the value of the limit and not where we are taking the limit.
no, L is what x is approaching basically.
Okay.
I put the L equal to 2 there.
Yeah, exactly. So that perhaps is a mistake. You should correct that.
But
Are you saying that the value of the limit is also 2 and x is also 2? Is that what you're saying? X is
no,
approaching
we're just
2?
saying that x is approaching L. X, the input, right, is approaching L either by increasing to approach L or decreasing to approach L.
Okay, okay.
Right. So yeah, so there are just two ways to write it. We either limit as x tends to 2 minus, or limit as x tends to 2 plus for the left side and the right side specifically. And yeah, so now I'm just gonna show some examples again. So we have this again. Now this function is the absolute value function. Whenever you input some value x, it outputs the absolute value of x. Now, well, we can find the value at x equal to 0. What's the value at x equal to 0?
Zero.
Yeah. It would be 0 because we can just plug in 0 into the function, and we see that the absolute value of 0 is just 0. And so, but now in this case, the left-sided limit would approach 0, right? The input variable would approach 0 from the negative number. So what would be the left-sided limit at x equal to 0? Anybody? Um, so yeah, remember the left-sided limit is when the input variable approaches zero, or in this case zero. So x approaches zero from the left-hand side. What value does the function approach? Remember the definition of the limit, basically, from the definition, so from what we define limit so far. So what would the function approach as x approaches zero?
0.
Zero.
Yeah. And how about from the right-sided limit?
Also zero.
Also zero. Yeah. Does everybody agrees with that, right?
Right. I mean, the values are perhaps negative and positive in these two cases, but there is no doubt that those values are approaching 0 from either side.
Yeah. So yeah, so if the left-hand side limit and the right side limit are both zero as x uh, approaches zero from either side, what would be the limit as x approaches zero? Not the one-sided limit, just just the limit of the function.
Zero.
Why?
Because that's what the function approaches from either side.
Yeah, so since it approaches it from either side, the limit should just be the same as both or either of them, right? And yeah, that's essentially that's correct when we say that when the values of the left side and the right sided limits are the same, we can say that the limit of the function is the same as the left or right side limit of the function at some as x approaches some specific value. Right? So we have left-handed and right-handed limits are zero, and we say that the limit as at x equal to zero of the function is zero. Okay. So now in this next slide, I have another function, and this is a piecewise defined function. I've defined it differently for x less than 1 and x greater than 1. So again, the same thing. What would be its value? Left side limit and right side limit as x approaches 1 from either the left or the right side.
So you'll go first from the left-hand side.
Yeah, first from the left hand side, let's say. And how about the value? The value is pretty easy to find.
From the left-hand side, it approaches E, and from the right-hand side, it approaches 1.
Approaches 1. Yeah. Okay. Does anybody disagree with that? So yeah, it seems to approach E from the left-hand side. Seems to approach E, and I believe it gets closer and closer to E, but it does not ever reach E. Right. And from the right-hand side, it seems to get closer and closer to 1 as x gets closer and closer to 1. So from the right-hand side, we can say it's 1. Okay, now, how about the limit at x equal to 1? The limit of the function f of x as x tends to 1.
There's a discrepancy.
Yeah.
It's D&E because it doesn't approach the same number from both the left and the right side.
So you're saying, yeah. So we have that it's it could be D&E because the left and right side do not approach the same value. Does anybody have a different answer? Does anybody think otherwise?
I don't think we can, because the definitions are pretty. You told us
Pretty,
not to not to think like that. You said that they have to approach the same value for the limit to exist.
yeah. So they say since we just say it does not exist because it approaches different values from the left and right hand side. So it doesn't approach a single value from either side. So we can't say the limit exists. Right. So we said that it's D&E. Now, from these previous two um, functions, can we find a condition for the limit to exist? For example, if I give you a random function and some value, okay, where the function may be defined. It doesn't have to be defined. It's just a value, okay? Um, and I ask you to find the limit of the function as its input tends to the given value, right? Now, what would be the condition for this limit to exist? Based on what we saw in the previous examples.
The graph has to be continuous, like it can't break off at any random point.
Okay, so that's interesting. But we haven't really gotten to what it means for a function to be continuous, right? Can we based on what we saw in the previous examples, can we see what based on what we just saw today, can we say what will be the condition for the limit to exist based on what we saw just right now? Okay, well, it might be a little tough. So, uh, we saw that one example for which the left hand and the right hand, the left side and the right side limits, that we saw one where they do match, and in that case the limit existed, and we saw one where they did not match, and so the uh, limit and in that case the limit did not exist. So um, I think we can say with enough confidence that when both one-sided limits exist, right, and they're equal to each other, then the limit will exist. Otherwise, the limit won't exist. Now, can now just going through your head to make sure this works for every single function we've seen so far, or any limit we've this any limit we've seen so far. Now, it seems pretty obvious for most limits, right? But then if we look at sine uh, 1 by x, if we look at sine of 1 by x, do you remember that rapidly oscillating function?
Can you show the graph again for sine 1 by?
Yeah, I can. 1 second. It's a bit bad. Right here. Sine 1 by x. So does this condition we just made that both both one-sided limits must be equal, Does that condition work for this function? Basically, can we find what are the left and right hand side limits for this function at as x approaches 0 from either side? First of all, let's start with left um the left side limit.
For both, it's undefined, right? So isn't that the same for
Yeah.
both?
So
Yeah.
yeah, so it was, as we saw, it was undefined, the limit, and for both left and right hand sides, it does not exist. So does our condition work here?
Yeah.
Yeah, because we said that the left and right side limits must exist, and in this case, they don't exist, right? So um, it just we say that the limit does not exist, so it fits our condition. Yeah, let me just go ahead. Let's go back. Okay, we say one-sided limits must exist and be equal to one another. Okay, now yeah, let's go ahead. Now this is something, we've seen this actually, but I'm coming back to it because I mean, now. What if the function increases arbitrarily? So, basically, what happens as the value of the function tends to infinity. So, and by this, I don't mean that what happens as um, x tends to infinity. I want to know what happens to f of x, the value of the function. I want to know what happens to, can we say something special for the limit if the the value of the function f of x grows arbitrarily large as x tends to a finite value, right? So that's currently what I'm talking about. So we call these infinite limits when f of x tends to infinity. So we say that infinite limits do not exist, even though we may not write it this way. Because um, suppose, so first of all, if we remember the definition of limits we introduced previously, can anybody tell why we say infinite limits do not exist?
Go ahead, Abdul.
Maybe because that infinity itself is a representation of unlimited um numbers or whatever, I guess.
Yeah, basically, there's no real number, right? That when we say that the limit exists, right, when the value of the function, in this case, let's just say it doesn't have to be a function. When we say the limit, right, the value we're monitoring, as x tends to some specific value, in this case, let's say a, as it grows as it tends to some real number. When it tends to some real number, we say that the limit exists. Now, although it's not, it increases arbitrarily as it gets closer and closer to a. So as x, suppose we're saying the input variable is x, as it gets closer and closer to a, we say that it increases arbitrarily, so it doesn't approach any real number, right? So we just say that um, we just make the connection that infinite limits really are DNA. So, but we do make the distinction between, I mean, not the distinction, we do identify the special case when the limit tends to infinity. It's a special case of the limit being the limit not existing, right? It's a special case of that because, well, we can say that it just grows arbitrarily large. We don't know what the value of the we don't know what the um, behavior of the function is, behavior of the limit is, but we do know as the input variable gets closer and closer to some a, this gets arbitrarily large. So we just
I
say
think
that.
sorry to interject, but I think what Apurva is trying to say is that there is a difference in meaning as to how sine 1 by x behaves when x
Yeah,
approaches 0 and a function like, let's say, 1 by x behaves as x tends to 0. Although both of them, we can say that the limit does not exist, the shade of meaning differs slightly. 1 by x just grows arbitrarily large or small, depending upon where we are approaching it from. But the sense is not the same for the function sine 1 by x. Because sine 1 by x just basically can have any value between -1 and 1. We just cannot tell as x approaches 0, which is not the case with 1 by x. We know that 1 by x will become arbitrarily large as x approaches 0 from the right hand side. And it will become arbitrarily small, or the negative of which will become arbitrarily large as x approaches from 0 from left. Is that what you wanted to say,
yeah,
Apurva?
that's yeah, that's what I wanted to say. It You explained it very well. Yeah. But now let's just there are some examples again. I'll go quickly through this. This is too difficult. So the value of 1 by x squared uh, uh, as at x equal to 0, we can just say that, well, it's undefined because we don't know what the value would be, although it gives this this function, right? Although as you get closer and closer to 0, it grows, you know, our well, we believe that it grows arbitrarily large, but at x equal to 0, we don't know what it is. There's no The function does not have a value, so we can say it's undefined. Specifically, though, yeah, it we can say that it's. I mean, we can't really say that the value is infinity. We can say that the value is. I mean, uh, we can say that the value grows. I mean, the value of the function grows arbitrarily large as it gets closer to 0. But we can't say what the value is at x equals to 0. So we just say that it's undefined, like always. Now, again, left hand side, left side limit, right side limit, they'll both be the same, and they'll specifically be infinity, right? Because it's growing arbitrarily large as it's getting closer and closer to 0. And now that we have the left hand side, the right hand side limit, what will be the limit of this function as x tends to 0 based on the left hand side and right hand side limits? Anybody? It's
Undefined for both.
Undefined. No. Okay. So yeah, the left we saw the left side limit and the right side limit is well, it really it does not exist, but specifically it's infinity. So it tends to infinity as x tends to zero from either side. But I'm wondering what would be the limit as x approaches zero from either side.
I would say this does not exist.
Does not exist. Why?
Well, because infinity is not a real number.
Okay. So just as we said for the one-sided limits, can we say that this one is also this one does not exist, but is a um, but it is infinity? Does can we say that the limit at x equal to zero is infinity? We know that it does not exist, but can we say that it's the special case of infinity? Yeah, go ahead.
I think so. Arav, go ahead.
So, like we defined, when from both right and left it's approaching the same number, the limit should exist. But in this case, the number that it's approaching is not doesn't exist. Infinity doesn't. So it's kind of like a contradiction, right? So I think we could say it's a special case.
So yeah, so are you so you think that uh we can say that it's infinity, not just we obviously we can say that it does not exist, but can we also say that it's infinity?
Yeah, special case.
Yeah, I
Special
think so.
case? Yeah, okay. If um yeah, so I guess we can say that because it uh they both approach this they're both special case, and so they don't approach the same number, but they're both infinite limits. So we can say that when it approaches from the point is when it approaches from either side. Okay, so when however you're approaching uh, x equal to zero, right, from the left or the right, any way you're approaching, it doesn't matter. It will always tend to infinity. So we can say that the limit is infinity. Right now, but how about this function f of x equal to minus 1 by x? Now, we know again the value will be undefined at x equal to 0. And the left-hand side limit will be positive infinity because it approaches positive, it increases arbitrarily as x approaches 0 from the left. But as x approaches 0 from the right, it decreases arbitrarily. And so the right-hand side limit would be negative infinity, minus infinity, right? Now, what would be the limit of this function as x tends to 0?
Go ahead, Arav.
This would be undefined because now they're not approaching the same number.
So
But
by undefined you mean DNE?
Yeah, I do.
okay, so it'll be dne but not infinity. Will it be infinity?
The infinities are on opposite sides of the, like, one is a positive one is a negative one. So can we say that they are not the same number?
Yeah,
That's
I
right.
mean they don't we can't say one from one side it approaches positive infinity, from one side it approaches negative infinity. So um it doesn't approach a single infinity. Now this feels weird to say because infinity is not a number, but it doesn't approach they one increases and one decreases arbitrarily. So they do not approach some, I mean they don't have the same behavior as x tends to 0. So we can just say that the limit is undefined or that the limit does not exist. and specifically that it's not infinity. In this case, it will not be infinity, but in the previous case, we saw it will be infinity. So yeah, we've seen a bunch of weird functions. Okay, weird. Um, very. Some are weird. Some are normal. We've seen them before, but they all have. Well, they can be all tied into one thing, and that's continuity. Now, we heard this word a few times before. What is continuity? Now, I want everybody to just think about that. What does it mean for a function to be continuous, right? And I'm gonna pull up a uh, another tab. 1 second. Okay. Does everybody see my screen?
Yes.
Yeah. Okay. Um. So I'm gonna. Uh, so now, when we think about continuity, at this point we want to see specifically if a function is continuous at a specific point on on the graph. Uh, Now, if I ask you the function, about this function, we've seen this before, or x minus 2, say. Now, can we say that this function is continuous at, say, um, x equal to 4? Is it continuous at this point?
Yes, it is.
Okay. It seems to be continuous at this point. Great. Now, how about if I do how about if I do this? Okay. Now this function, is it continuous at x equal to 4?
No,
Why not?
because there's a hole. So, um, it would approach it infinitely from the left and right side, but not actually touch that point.
Yeah. So what would be the value at x equal to 4?
Undefined.
Undefined, right? So we can see that the graph is not continuous. Like I heard previously, there's a break in the graph. Now that's correct. In this graph, we see that there's a break right here, at 4, 2. So we can say that it's not continuous, right? So now, there are many things I can do with this. Now, how about this function? This is interesting function. 1 second. Um, okay, so now this function is, uh, I mean, it's pretty, uh, and it's quite clearly this function is discontinuous. There's a huge break in the graph, right? But now, okay, I have another function. How about this function? Sorry. What this function? The absolute value function. Is it continuous at x equal to 0?
Yeah.
It's continuous at x equal to 0. There's no break in the graph?
No. Wait, is there?
But
Yeah. No,
the
it's
graph, if the graph changes direction, don't we say that it's a discontinuous function?
Okay. Um, so okay, this is interesting. So it's now as we get closer and closer and closer to 0, okay, from the left hand side, what will happen? Um, is there any break in the function as it gets closer and closer and closer to 0?
No.
Um, no break in the function, right? And how about from the right side? Is there any break in the function?
no.
No.
No. Now, you know what? We can actually try this. If I just zoom into this point, we can see that, and I'm zooming in a lot, but we can just see that there doesn't seem to be a break anywhere. Right now, at 0, what happened? It's defined at 0, right? As we saw previously. But so is it continuous? Is there a break? So we heard that continuity can mean when a graph is, when the graph breaks at some point. So a discontinuity specifically. So is there a break in this graph? And
No.
you can take your time. Yeah.
There's no break.
There's no break. There's How about at x equals to 0? There's no break. Does it gets closer and closer to 0 from either side, right? But it doesn't break at 0. So sorry, I'm just this is just something to think about, I think. And I think it's been an hour now, so it's just something I want to leave you guys with, and just think, like, if I on any different function you can find, is it uh, especially this function, okay, is it uh, continuous at x equal to 0? And then maybe we can think about this and then maybe you can think about what happens if, how can we tell if the function is continuous or not at some point. Okay.
Right. I think as it turns out, I think this is related to our discussion about whether the limit exists or not. And
Yeah.
so, so yeah, I think we perhaps have come to this, this kind of questions. So maybe we can again discuss it on the group. Sometimes it may feel like this is overly, sort of wordy or prolix, or we're just spending too much time on that. But unfortunately, some of this part we have to get right, and so we'll move more quickly once we have all these things in place. Cool. Yeah, so any more functions you have on Desmos? So everybody, by the way, knows about Desmos and GeoGebra, right? You guys should play with those two. It's
Yes.
very
I
useful. Yeah.
Yeah, we use them in school. As in, We use them for like maths projects and stuff. Like we use GeoGebra for everything almost.
Yeah, it's
Yeah, I
very
mean,
useful.
I think it's very good to explore. I mean, it's much more than a graphing calculator, in my opinion. If you look at what various people have created as like their artwork, and obviously a lot of math and geometry lessons in that, but it's pretty cool. I mean, I personally like it very much. Cool. All right, so we will. I mean, if you have any questions, we can definitely talk about that. But otherwise, I think we should, like Apurva said, yeah, go ahead, Apurva.
Oh no, I clicked it by accident. Sorry.
Oh, okay, no problem.
Yeah.
Um, yeah. So, should we end the meeting then? Let me just.
Cool. So, yeah. All right. So, yeah, if there are no questions, I think we should leave everyone with this thought, about, um, getting the idea behind continuity right, so that we can make a little more progress next time when we, uh, finally conclude about limits and then start talking about perhaps more interesting. Uh, I mean, all of this is interesting, but maybe more interesting things like derivatives. Cool. All right. Thank you, everyone. Please, contribute on our channel. If you have any questions, any comments, please make them there. And see you next time.